that E is irrational. There are several proofs, but here is my proof. It's more convenient to prove that this is rational. Of course, if E is irrational, then this is vice versa. And if you go to Maple, lo and behold, you get a beautiful, beautiful continuous fraction. 1 over 2 plus 1 over 6 plus 1 over 10. So it's obviously a pattern. 1 over 18. So it's 2 plus 4n. But now it's not so easy. So obviously you can make a conjecture and define this to be x. Obviously, by construction, it's an infinite continued fraction. It's irrational. Then it takes some, a little bit harder, but still not too hard, to prove that this x defined by this continued fraction is equal to the familiar. But you can also do it empirically first. Maple has a beautiful command called identify. So you can compute 100 digits for this infinite continuous fraction, and then do identify, and Maple will tell you that it's e minus 1 over e plus 1. So, at least, and that's my dream. Why stop here? So here is the proposal to prove, at least, if you're really lucky, you get this. But at least to be able to prove no new interesting continued irrationality proofs. Take any infinite, take any polynomial, for example, n squared, and construct the following infinite continuous fraction. And get Maple to evaluate it to 100 decimal digits. Then go to the database that you did before, continue billions of interesting numbers cooked from e+pi and gamma, and see if it's there up to 50. And if it is, you are in luck. And then don't tell anybody that, and suppose it will turn out to be e squared plus pi cubed. Don't tell anybody, so please keep it a secret how I did it with the database, and that by luck I found one of them. Have a friend, hopefully famous, make a conjecture that e squared plus pi cubed is irrational. And wait 10 years, let people think it, and then come up with a proof of the blank conjecture, the e squared plus pi cubed. And then you just come up with this. And with computers you can do so much faster. So much faster, and so this is my dream of being famous, by systematically having a database and having stuff like this. And you don't need to stop at polynomials. You can do quadrupolynomials. You can do lots of crazy things. And who knows? Maybe you luck out and get it. And sometimes it's good not to have numbers. Numbers are hard to count, to handle empirically. But e to the x is a function. So let me now tell you my favorite, the first and still my favorite proof that pi is irrational. This was a big breakthrough by Lambert in the mid-17th century. And I want to understand Lambert's approach and teach it to a computer. This is my dream. As you know, probably the big problem of squaring the circle was open for 200 years. And for this you needed something more. You needed to prove that pi is transcendental. And this was Lindemann. Proved it in 1882. He proved that pi is not a solution of an algebraic equation with integer coefficients. And by this, he proved a 200-year-old, at least, problem of that it's not possible to, with a compass and ruler to giving a circle to construct a square with exactly the same area. But that was a big step to outside. So how did Lambert do it? He looked at the function tangent of x, and he worked very, very hard to find a continuous fraction representation for this with x. And he found out that you have a variable x, so you have a little bit more structure. And so on. Right now, Maple can discover it all by itself without Lambert. You go to Maple and you do convert. Now you need to do Taylor. So you Taylor tangent of x at 0, take 50 terms at penny, and then x, a construct x, semicolon. Do this command. And you get the first 20 terms of this. And obviously, you see a pattern. And to get a rigorous proof is an exercise once you know it. Knowing the structure, that's the important thing. Once you have it, it's relatively easy to prove. And then Lambert reasoned as follows. Suppose that pi is a rational number. Suppose that pi equals a over b for some integer a or b. So you plug it into here and get tangent of a over b equals a over b 1 minus a squared over b squared over 3 minus a squared over b squared over 5, etc. Now you have to be a little bit careful. This is not a simple continuous fraction. The fact that an infinite continuous fraction is automatically irrational only applies to simple continuous fractions. Here the numerators are no longer 1, but they are integers. But Lambert proved the simple lemma. If you have such non-simple continuous fractions, but if eventually, starting at a certain point, the numerator is less to the denominator, then it's also irrational. So that's the simple lemma. So since A is fixed, and B is fixed, possibly very big, since you divide by 2 n plus 1, sooner or later, the numerator will be less than the denominator. And what that happened is true forever after. So using this lemma, that this infinite continuous fraction had this property, he proved that if a over b, if pi would have been, sorry, pi over 4, if pi over 4 would have been a ratio to integer, then tangent pi over 4 would have been also irrational. But as I'm sure you know, tangent 45 degrees is 1. Since 1 is not irrational, is irrational, then QED is a proof of contradiction. By the way, the arctangent, you can also say, another possible candidate proof is to use this fact, that pi over 4 is arctangent of 1. Arctangent of x also has an infinite continuous fraction, but not a nice one, nothing with this property. And if you do it, you get the famous continuous fraction for pi that does not prove that it's irrational. So for this case, this is useful. You have to go in indirect way. But suppose that we didn't know it. Suppose we're doing things from scratch. So that's another plan, and maybe more promising, because now you're working with functions. Cook up infinite new functions on x. So take any polynomial, or quasi-polynomial, or anything that you can write down. For example, n squared, define a function f of x. 1 plus x over 1 plus x over 2 squared plus, plus x over 2 cubed plus x over to the power 4. So define this function. Now, compute the first 100 terms in the Taylor expansion. And then empirically guess a differential equation. So if we would have done it for this one, suppose we didn't know that tangent of x was this. Suppose we would have just defined this to be f of x. We would have gotten the Taylor expansion. Now, the Maclaurin expansion of the coefficient of tangent x are not nice. There's no closed form for this. But the computer could easily, empirically, could have conjectured a nonlinear differential equation. Sorry for f of x. So empirically, just tell it to guess, write a little program, guess nonlinear PDE, ODE. So, and then you can solve it, and y of 0 is 0 because the coefficient, that's x. And when you solve it, you get tangent x. But suppose that you didn't. You can make up a paper. Let blah 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 be a solution of the following nonlinear ordinary differential equation. Then y of 1 is irrational. And then we follow immediately from this. Because we go backwards. We start with an infinite continuous fraction featuring x. Then empirically, and then that can be made rigorous once you know it, it's not hard to prove it rigorously, this nonlinear differential equation satisfied by this infinite series. And then automatically, when you apply x equals 1, you get a simple continuous fraction, and you get that y of 1 is irrational. So this is the plan for proving. Let me conclude with a heartwarming story about. So let me tell you what's open. Very, very little is known. What's known is that sigma, this is known, is irrational. Because Euler proved that it's equal to pi squared over 6. And also this is known because it's pi to the power 4 times something, some number, Boolean numbers. So the so-called zeta of an even integers are all proven, sorry, not known. I should not use the word known, stupidly. Are all provenly, rigorously proven. But until 1978, it was wide open. But zeta 3 is to prove, to give a formal proof that zeta 3 is rational. And then a French mathematician, 64-year-old mathematician, who stopped doing research when he was at the early 30s, because in France you get tenure early, so there's no pressure to publish, and he was interested in many other things like politics, so he didn't publish anything. And people always thought he was dead wood, but apparently he did think of hard problems. And all of a sudden, after not publishing for 25 years, he came up with a proof of this. Of course, nobody believed him, and people made fun of him. People saw it was a prank. But no, he was right, and he proved that this is. And he had a beautiful, beautiful approach for proving it. I don't have time to do it. But this is only one isolated case. You'll be very, very famous if you can prove that a 5 is rational. Nobody has any proof. And in general, for any odd value, find the proof, open problem. And once again, I think my database approach, not focusing on one specific constant at a time, is much more promising. Try to prove irrationality of as many numbers as you can. And if you're lucky, one of them will be among the billions and billions numbers in your database. And another thing that I would love to prove is irrational. Perhaps the simplest is a Catalan constant. I already mentioned gamma. It's also come up in physics. It's the alternating sum of the odd integers. Nobody has any clue how to prove this. Now, one approach for proving this, IRRATIONALITY's approach, was to come up with a sequence of rational numbers. So you have alpha, a number you want to prove is rational. Construct explicitly a sequence of rational numbers, an over bn, go to alpha. Of course, the best such sequence is the continuous fraction expansion. So you can expand the continuous fraction expansion of Z5 of this. And if you did infinity, then you get the best sequence of the so-called partial quotient. But then the circular reasoning, you don't know a priori, you do know, but you don't have a proof that it's infinite continuous fraction. So that unit continuous fraction, unless you can detect a pattern, is not good. So IRRATIONALITY found out another way of coming with explicitly an and bn integers such that the sequence of ratios goes to Z3 in his case. And what he needed is the so-called irrationality measure. He needed, of course, it's easy enough to come with sequences, but they have structure and they have the property that the difference was some constant, this was the crucial. Delta, I need the delta to be positive. So if you use IRRATIONALITY's approach, you can easily get similar sequences for Catalan's constant, for Z5, for Z7, but unfortunately you get delta to be negative. It's still a terrific approximation. If you get 0.5, it's still very, very fast approximation. From a number, numeric analysis point of view, it's very, very good. But to prove irrationality, it has to be bigger than 1. And IRRATIONALITY found 0.08. So another approach, if you don't like continuous fraction, or if continuous fraction is hopeless, is to come up with some explicit sequence of rational numbers where a sub n and b sub m are given algorithmically, and to prove it. And make sure that delta is this. And once again, you can do it systematically. Once again, you can do it for many, many constants, for many possibilities. And then the computer empirically found out what is the delta. And if it's less than 0, you discard it. And if you're lucky, after running for 2 years, you get something interesting, you have a nice paper, and possibly a breakthrough. So that's another possible way of proving irrationality. Then again, you never know. Maybe it's true, but unprovable. I mean, too hard to prove. You never know that. Let me conclude with my favorite bad proof. As you may know, I don't believe in the law of excluded middle. Classical mathematics is flawed because it believes, even for infinite sets, that it's either, everything is either yes or no. So here is a proposition whose proof I don't know, I like very much, but it's not a proof. There exist irrational numbers, A and B, such that A to the power B is rational. Can you come up with two irrational numbers? No, you cannot come up with two irrational numbers. Actually you can, but not with this proof. But you can prove that they exist if you are a classicist, if you believe in the law of excluded middle. That is, of course, false. And here is a beautiful proof, although it's flawed. Consider the following two candidates. A is square root of 2 to the power square root of 2. And B is the square root of 2. We already know, we had 3 proofs that square root of 2 is irrational. So it has case 1 and case 2. Case 1, A is irrational. Then you are done. Because since square root of 2 is irrational, square root of 2 is rational, if A is irrational, we found, sorry. No, it isn't. No, it isn't. Right. Yeah, case 1, A is irrational. Now I'm confused.
You were saying A is rational.
And if it's rational,
Yeah, irrational.
No, it's correct. So yeah, it's correct. If A is irrational, then you are done, and if A is rational, then you are done already.
Yeah. Oh, yeah, right. Yeah, if A is irrational, right. If stupidly. Yeah, if A is irrational, then A to the power B is square root of 2 to the power square root of 2 to the square root of 2. Square root of 2 to the power 2, 2. Yeah. So, yeah. In case 1 is a hard one. If A is irrational, then it is. In case 2, A is rational, and then we are done. But of course, this is not a legitimate proof because it uses the law of the excluded middle because this is infinite. The fact that the statement blah 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 is irrational is an infinite statement. It means you have to go through the whole set of all infinite integers and check. There's no algorithm to go and check for each and every 2 pairs of infinite integers. So it's a priori meaningless. Many statements can be made a posteriori meaningful by getting a proof. But that's an example of a beautiful proof that is not completely legitimate. Thank you very much for your attention. And I hope you take attendance and
Yep, if anyone didn't sign in, I've got sign in sheet.